Hi there, if you're waiting, welcome to the first of our Sustainable Future Speaker Series for the season. We're going to give folks a few minutes to get oriented in the webinar before we get started. Hi to anybody who's just joining us. Welcome to the webinar. We're going to give folks a few minutes to get situated here before we start in with introductions and tonight's speech. Hi, and welcome everyone. My name is Kevin Fingerman, and I'm going to be giving a bit of an introduction to this series, and then we'll pass it off to a colleague to introduce tonight's speaker. Welcome to the first webinar in this fall's Sustainable Future Speaker Series here at Humboldt State. This series has been running since 2005, and these are interdisciplinary lecture series that has stimulated a lot of interesting conversation and collaboration around issues related to energy, environment, and society. All the events are free, open to the public, and are sponsored by a collaboration between the Schatz Energy Research Center and the Environment and Community Graduate Program here at HSU, as well as the College of Arts and Humanities and Social Sciences. This fall, we're really excited about our series. We're presenting 8 different speakers, all via webinar, ranging from telecommunications resilience on the Redwood Coast and using data to drive public health decisions to Latinx environmentalism and decolonizing our climate change strategies. We're also hosting 2 talks focused on Palestine, the first of which will be given 2 weeks from this evening, Thursday, September 17th. Dr. Omar Tesdel will be speaking to us from Palestine, where he is working on open science methods for building agroecosystems. For this coming talk, Dr. Tesdel's talk only, we'll be meeting it at 7 p.m. Pacific time rather than the typical 5:30, because that is 5 a.m. for Dr. Tesdel, as he will be joining us from his home. The latest information on the Sustainable Future Speaker Series, as well as SCHOTT Center research webinars, can be found at shottcenter.org/events. I've got a couple of housekeeping points to do with running this webinar for the evening. If you'd like to ask a question of tonight's speaker, please use the Q&A box that you'll see at the bottom of your Zoom interface, rather than the chat box, because that is the easiest way for us to manage the questions. Tonight's presentation will be followed by a Q&A, and Dr. Nicas may also take some clarifying questions during his talk tonight. If you have any technical difficulties, on the other hand, please post those into the chat box, and my colleague, Maya Kelly, will help you, or will attempt to help you, to resolve the problem. A recording of this talk will be available later in the fall at shottcenter.org/events. And I'd also like to mention at this time that a copy of our popular talk from this summer on the Thwaites Glacier and with members from the US Antarctic program is available for watching online. I'd like to now hand things over to my colleague and friend, Nick Lamb. Nick's a research scientist here at the SCHOTT Center, and he has expertise on topics related to energy access and air pollution in developing countries, and he'll be introducing tonight's speaker. Thanks.
Thanks, Kevin. It's my great pleasure to introduce Dr. Mark Nicas. Mark is an Emeritus Adjunct Professor at the School of Public Health at UC Berkeley. His academic research has been in 3 areas: the exposure and risk assessment for pathogens, including those related to tuberculosis, valley fever, and influenza, mathematical modeling of exposure intensity to airborne chemical toxicants, and the variability in the efficacy of respiratory protection. Mark has been a professional industrial hygienist for over 40 years and is a certified industrial hygienist. He received a PhD and an MPH in environmental health from UC Berkeley and MS in genetics from the University of Wisconsin, and a Bachelor in Science and Biology and Chemistry from the City College of New York. So with all that out of the way, I'll add some personal remarks now. Mark's exposure assessment and control course at UC Berkeley was a class that nearly all graduate students working on air pollution and environmental exposure passed through. It was among the most influential classes that I ever took, and I think based on how many former students are in the room right now, others would agree. I TA'd for his class like 4 times, so I'm pretty sure I'm an authority on this. And for those students in the audience, or former students to the audience who took Mark's class, his exams, or had him on a committee, the tables have turned. There is a Q&A, and with that, I will turn it over to Mark.
Thanks, Nick. Okay, well, I do much appreciate being invited to give this presentation about the inhalation transmission of COVID-19. A large share of the information I'll be relaying is not new whatsoever. I dare say it has been well understood for decades. But for some reason, many infectious disease professionals find it hard to believe that when particles containing an active respiratory tract virus are emitted by a person infected with that virus, those particles can be inhaled by other people and cause secondary infections. I also much appreciate being invited to give this talk because Nick has promised me a free pizza as a reward. Now, when
it's coming at 7.
Yeah, right. Now, when I used to teach classes at Berkeley, people would ask questions as they arose, and that's a good way of doing it, but you can't really do it in this format. So what I'm going to do is that I'm going to present certain chunks of information, and then I'm going to pause and ask for questions, and Nick will be the gatekeeper of those questions. And if anyone has posted questions online in the Q&A portal, then I'll answer them then and there. And then at the end of the talk, of course, you can ask as many questions as you want. If I don't know the answers, I won't fake it. I'll say as much. And finally, before I start, I want to note that there are online video recordings available of a workshop about the inhalation transmission of COVID-19 that were that were organized by the National Academy of Sciences and put on last week. And there's a link to these video presentations that I've sent to Nick and will be made available to anyone who registered for this particular seminar. So if you want more details about things that I've been talking about, I think that looking at those recordings would be a good place to start. So let me try and share my screen. And very good, there it is. Okay, so that's me, okay. And why is not that There we go. Okay, so I just want to briefly say what I'm going to be talking about. I call the SARS-CoV-2 virus just SARS-2, and I'm going to explain it's containing fluid particles emitted from the respiratory tract. And so I'm going to discuss some basics about particles and their behavior in air. And then virus and air associated with these particles can be removed by several different mechanisms. And I'm going to discuss these mechanisms. They do relate to ways that we can reduce the virus concentration in air and thereby reduce infection risk. And then the emission of virus and inhalation of virus can also be reduced to different degrees by different kinds of face coverings, face masks and respirators. And I'm going to discuss face masks and respirators as well. So particle sizes. The behavior of a particle in air depends on a characteristic called its aerodynamic diameter. If you had a sphere of water with a physical diameter of 1 micron, the particle's aerodynamic diameter would be 1 micron. If the sphere of water were 2 microns, the particle would have an aerodynamic diameter of 2 microns and so forth. And this is a way to describe particle behavior in air depending as a function of their aerodynamic diameter. Now, because respiratory tract particles are primarily water, they're not pure water, but they're primarily water, I'm just going for simplicity to equate their physical and aerodynamic diameters. Now, this is a slide stolen from the EPA or borrowed, and it just basically tries to show the scale of things. So it shows a human hair, which is 50 to 70 micrometers in width, according to this diagram. And we can all see a human hair. But when you have these very small particles, like let's say PM2.5, around 2.5 microns or less, you can't see these. I mean, as individual particles, you cannot see them with the naked eye. You need a microscope. And the same would be true for PM10 particles, about 10 microns. So we're talking about particles that are emitted from the respiratory tract, most of which you can't see. But it is true that if you had a high concentration of very small particles in the air, they would scatter enough light so that something would be visible. But really, as individual particles, you cannot see them. So all particles that are less than 100 microns in diameter can be inspired into our nose and mouth. Now, particles that are between 20 and 100 microns cannot penetrate past the larynx, so they stay in the head airways region. Particles that are less than 20 microns can get through the larynx, and if they're between 10 and 20 microns, they tend to deposit in the tracheobronchial region, so the large airways in the trachea. If the particles are less than 10 microns in diameter, they can reach all the way down to the alveolar region of the lungs, which is the area of gas exchange in the body. So again, we can take into our body, inspire all particles that are less than 100 microns, but only a certain fraction of them, the smallest, can actually make it all the way down to the end airways. Now, if cells with membrane receptors for virus are everywhere throughout the respiratory tract, and it looks like they are actually, then all particles that are less than 100 microns can be inspired and cause infection. And that would be true for the nose and the mouth and the trachea, maybe in the large bronchi in the end airways region. Now, it is also true that the most concentrated sort of density of receptors appear to be in the alveolar region, which is actually an area where you would have pneumonia setting up, as I understand. But pretty much any place in the respiratory tract, this virus can deposit, and whether it causes infection or not depends on other things. Now, the infectious dose of SARS-2 virus, the number of particles that have to be received to infect the host, is not yet known, and it likely varies between individuals based on genetics, sex, age, and health status. Now, what I just said about the infectious dose is kind of simplistic because it implies it's a threshold number. In other words, if you receive a certain number of virus at or above this threshold, you'll be infected with certainty, but if you don't receive that number, you receive a lesser number, you're not going to be infected. And it's really more realistic to think about it this way. As you increase the number of pathogens you received, you increase the probability of a successful infection. The thing is, for the SARS-2 virus, that probability of infection for any given dose is not known. So there are lots of unknowns. A bit later in this talk, I'm going to discuss something called the Wells-Riley infection risk model, because it is being applied now to COVID-19 transmission. And in that model, it is assumed that there is a threshold dose and that is the same value for everyone. And really, that's an overly simplistic way of thinking about it. Now, it's not known if you take the same dose of virus and deliver it to different areas in the respiratory tract, it's not known if the virus would be equally infectious. I mean, if you delivered, make up a number, 100 virion particles to the alveolar region, maybe that's more infectious than if you delivered 100 particles to the throat. The information available to answer that question is just not known. And what's also not known is something about dose severity. In general, for pathogens, the more pathogens you take in, let's say inhalation, the more severe the response will be. And the thinking is that's probably true for SARS-2. You know, the higher the dose, the more severe the infection. But no one knows anything really about the nature of that severity dose response. There are lots of unknowns about the SARS-2 virus. So when we speak, cough, talk, sing, sneeze, we emit a whole range of particle sizes from our nose and mouth. And for nose breathing, this is from the nose, and for your mouth, it comes out of your mouth too. And these particles can range from less than 1 micron to over 1,400 microns. So you can see a 1,400 micron particle, but you can't see the 1 micron particle. So there's a whole range of particle sizes. Now, there have been a number of studies that look at the distribution of particle sizes in a cough and also during speaking and singing. And in one particular study I've referenced here, and by the way, all these reference numbers are listed at the end of the talk in a PowerPoint slide, so you can go look at the study if you want to. The median particle size emitted during a cough and during speaking also was about 8 microns. Median, some parameters, means that 50% of the particles are less than that number, 50% of the particles are greater than that number. So you have a lot of small particles, and then various studies have found various numbers of particles emitted during a cough. This particular study found around 1,000, 2,000 particles emitted during a cough, and far fewer particles were emitted over the course of speaking, okay, when counting the digits from 1 to 10, 1 to 110 times. So other studies have found maybe smaller median particle sizes, but on the same order of the number of emitted particles. Part of the variability between studies is that you're using different subjects, and not everyone's the same, and they use different methods of visualizing or measuring the particle sizes. Now, the detailed characterizations of particle size distributions emitted by people with respiratory tract infections, and specifically COVID-19, that information does not exist yet. So we can't say that this information for healthy subjects, and these are healthy subjects in general, we can't say that that applies to sick people. On the other hand, we can't say it doesn't apply. So it really is the best information that we have available at the moment. So there have been some studies that have looked for the presence of different types of virus in different size fractions of particles. And so I'm going to mention 3 here. There was a study that was done around 2013 or 14, where they took people with influenza and had them speak and cough into a special apparatus that would collect all the particles that were emitted. And they separated these particles into what they call a fine fraction, which were less than 5 microns in diameter, and a coarse fraction, greater than 5. And then they used polymerase chain reaction assay to look for the viral RNA. And they found about 90% of the subjects emitted fine particles containing influenza RNA, and 48% emitted coarser particles containing it. But the most interesting statistic is that 90% of all the viral RNA copies, and that's basically the virus, 90% of all the virus, was found in these small particles less than 5 microns, and 10% in the other, the greater than 5. So the small particles had most of the virus. Now, there was a follow-up study published this year by some of the same researchers, and they didn't just look at influenza, they did that, but they also looked at seasonal coronaviruses and rhinovirus. And the nature of the presentation doesn't allow one to give percentages. But what they did find is that more virus RNA was found in the small particle fraction, less than 5 microns, than in the coarse particle fraction. And there was a completely different study published in around maybe 2013 or 14, where they again looked at people with influenza, and then they collected 3 different particle sizes, less than 1 micron, 1 to 4, and greater than 4. And just to cut to the chase, about 65% of all the virus RNA found was in particles less than 4 microns, and 35% was in particles greater than 4 microns. So if one looks at the actual particle numbers and sizes that are in a particle size distribution, what you see is greater than 95% and probably greater than 99% of all the fluid volume in respiratory tract emissions are in particle sizes greater than 5 microns. And this makes sense. You know, a 20 micron particle would have 1,000 times the volume as a 2 micron particle. So why do particles less than 5 microns carry most of the virus when they constitute such a small percentage of the volume? The answer is likely the site of origin of the particles and the highest titers or concentrations in given regions. The smaller particles, those less than 5 microns, tend to come from the deep lung, while the larger particles tend to come from the larynx and the mouth. And it could be that the virus concentration in fluid, number of particles per milliliter, is greater in the deep lung than it is in the larynx and the mouth. And so when you look at all the particles coming out, that's why you see the smaller particles carrying the most virus. Okay, so I'm going to pause here. I might be speaking too fast anyway. And I'm going to field any questions that you all might have.
I think we're okay to keep going, Mark.
So I'm as clear as mud. Okay, very good. All right. So the golden 6-foot rule. So we have all heard repeatedly, ad nauseum, I might add, that we should maintain a distance of 6 feet. I must say that the old Centers for Disease Control rule was 3 feet. They liberalized it to 6 feet. And the World Health Organization still recommends this 6-foot distance. Now, the reason for this distance is the belief among infection control professionals that being struck in the eyes, nose, and lips by droplet projectiles, which are also called droplet spray, is the major infection pathway. And then also there's a pathway called hand-to-face contact. What does that mean? That someone's has contaminated fingers because there's mucus on them and they touch a table. Someone comes along, touches that spot on the table, transfers it to their fingers. Then they stick their finger in their eyes, or they put their finger on the tips of their nose or on their lips, and that transmits infection. But it's this idea that this droplet spray, these sort of emitted particles acting as projectiles at close range and hitting you in the eyes, nose, and lips, where this hand contact is the major route of transmission. And in regards to droplet spray, it's also believed that the particles responsible for hitting you in the eyes, nose, and lips cannot travel more than 6 feet before falling out of the air. So that's sort of where it comes from. Now, there is no standard definition for what is considered a droplet, but it's now considered that particles greater than 5 microns can act as these projectiles. So they're called droplets, okay? But also recall that particles that are 5 to 10 microns can be inspired and can penetrate all the way down into the alveolar region. So a question to ask is, do all emitted droplets larger than 5 microns fall out of the air within 6 feet of their emission point? And the answer is no, they don't. So let's consider a droplet that's 5 microns in size. In preface, particles that are emitted from the respiratory tract, which are mostly water, lose a lot of their water pretty quickly. And so they will, within a second, shrink in size to less than 1/2 their initial diameter. I'm going to ignore this shrinkage and just assume the particle stays the same size. It doesn't really change the analysis much. Now, in perfectly still air, a 5 micron water particle will fall at the rate of 0.15 feet per minute. So if you were to emit it horizontally at 5 feet off the ground, it would take a little over half an hour to hit the ground. So it doesn't fall that quickly. Now, one of these studies that I had referenced previously found that the average expelled air velocity in a cough was 38 feet per second. And the average expelled air velocity during speaking was 13 feet per second. Now, those velocities are going to decrease, with time, but those are the initial velocities coming out. So a cough's airstream is going to cause that particle to travel more than 6 feet before it settles out of the air. So the 6-foot rule is sort of this ad hoc distance that was made up without really any quantitative basis for deciding that 6 feet was adequate. And that's just the reality. There was a different study performed, which was really a fluid mechanics analysis study, and it also had video imaging of the plume emitted during a cough. And what it found is that particles 30 microns in size would not settle out until they had traveled about 8 feet horizontally. And there was a certain quote that I took from the study that a particle 10 microns in aerodynamic diameter that was emitted in a cough would remain suspended in this cough plume meters away from the cougher, certainly more than 10 feet away. And the reference here, this reference 6, has a nice picture associated with it. And actually, the author of that study was one of the presenters in that National Academy of Sciences workshop. And in that workshop, her presentation, she has a very nice video recording of the plume as it travels a distance. So let me go to this. So I'm just trying to visualize it. So this person in the red there on the far left, they're the sick person in red. And here's a person facing them, that you can call that person a receptor or a susceptible person. And this diagram is trying to depict that as particles are emitted from the mouth, let's say in a cough, they're going to spread in sort of a semi-conical fashion. And the bigger particles here, in the big red dots, these are meant to be these sort of droplets. And it shows that some of them can strike the face, of the person opposite. And some of them may fall, are going to fall out maybe within 6 feet, the really bigger ones. But most of them are going to be suspended in the air by the time they reach the person, Now, in this diagram, they call this the direct contact. Well, they call direct contact people shaking hands, and this person being close to the other person might be considered close contact, I call it near field exposure because you're near the person who is emitting the virus. It's also called short range airborne route. So this is a setup. If you're close to someone, you can be hit with some of this droplet spray, but also you're subject to a high intensity of airborne concentration of virus-containing particles. So you're going to inhale some of these particles, and then some of these particles may strike your face. Now, if most of the virus are in the small particles, actually those probably won't strike your face because they're going to follow the airstreams around your face. The big particles will have inertia to go strike your face. But anyway, you'll be subject to both kinds of exposure, inhalation and direct droplet spray. The other part of the diagram, there's something called labeled indirect contact route. That's what I was trying to explain, where maybe the particles settle on a surface, or someone touches the surface with contaminated hands. Now someone else comes along and touches the surface and picks up virus on their fingers, and now those fingers get transferred to the eyes, nose, and lips. And then what they call here long-range airborne route, this is just the fact that the particles that are small, that are emitted, are not going to settle out very quickly, and they're just going to disperse throughout the room air. And therefore, anyone in the room is going to be exposed to these particles. The fact is, what the diagram shows, is that the closer you are to the point of emission, the higher your exposure intensity is going to be. So I'm going to go back a slide here. So actually, I'm going to repeat something I just said. So what's the utility of being, if these particles can travel more than 6 feet, what's the utility of remaining at a 6-foot distance? Well, one, there is less droplet spray exposure, because the further you are away, the more likely it is that the bigger particles are going to drop out before they can reach you. So that would make less droplet spray exposure. And the farther you are away, the less dilute, the more dilute that sort of cough plume is going to become, and so will decrease inhalation exposure intensity. So it's a good idea, actually, to remain at least 6 feet away from people, but it's not because you're not going to be hit by any droplets coming out as projectiles. So a different question is, if a 5-micron particle that can strike the eye, and that's droplet spray, why is that more infectious than if the same 5-micron particle is inhaled and deposits in your respiratory tract? It's almost an existential. There's no reason to believe that a particle that's the same particle striking your eye is going to be more infectious than the same particle that you inhale and deposits in the respiratory tract. Now, unless there were more cells with virus receptors in the eyes than in the head airways region, and I don't think that's true. So the CDC, the WHO, and most infection control professionals assume, and I mean assume, that droplet spray is the primary route of transmission and not inhalation. But when you ask them what proof do you have for this assertion, this assumption, they don't have any proof. It's a truism. It's an accepted truism, and it's likely not true. Now, something I thought about, you know, eye infections are not an outstanding feature of COVID-19. In fact, when you look at lists of symptoms of COVID-19, you don't see eye infections. So I was wondering, well, if the eye transmission pathway, this droplet spray to the eyes, is so important, why don't you see more eye infections? So to me, it argues against the eye being an important entry point. But I was talking to an optometrist today, trying to get my glasses fixed, and what she told me was that, well, you know, the eye has lots of defense mechanisms for you know, dealing with pathogens and stuff. You know, IgA antibodies, bathing the eyes. Well, I don't know what IgA antibodies do if they're not specific against the SARS-2 virus, but maybe there are defense mechanisms in the eye that limit the likelihood of eye infection. But the fact is, if something gets in your eye, there is natural drainage from the eye into the nasopharynx, so that is certainly a possible exposure route. Now, also about the mouth, you know, so the other thing about droplet spray, they talk about, well, you know, if it hits your lips, that's another portal of entry, which is also kind of curious to me, because it is stated that you can't get infected by eating food or drinking beverages containing the virus. So if you can't be infected by putting the virus in your mouth via food and beverages, why is the virus getting on your lips a portal of entry? Well, I can't figure it out. It doesn't seem consistent to me. All right, so before I launch into the next phase of this, are there any questions that I can try and answer?
Yeah, Mark, we have a couple questions from Marley. The first one is, particles 5 microns in diameter and smaller will stay suspended for at least 30 minutes, correct? Does turbulent airflow play a role in keeping small particles suspended in air for long periods of time?
Yeah, well, yes, they do, but the 30-minute, you're right, they do. And so, in fact, there's a different kind of equation one uses for when you have air in motion. You know, air in a room is never still. Air is always in motion. You might not feel it, but it's always in motion. So the fact is, it's not going to just settle in still air. It's going to take longer to settle. But there are other mechanisms now that compete with the settling, which I'll get into under the removal, and that is, unless you're in a sealed room, there's some kind of air exchange in the room, and that's going to be, you know, through doors, open windows. If there was a mechanical air supply system, there'll be air coming in and being exhausted. So there's these sort of the exhaust air is a competing mechanism to take particles out of the room air. It competes with the natural settling of the particles. So the particles, they might, before they can even settle in the room, they might be sort of whizzed out of the room by some kind of exhaust airflow. But yes, in general, the particles will stay suspended in the air longer than if they were in still air because of this turbulent air motion. So actually, I'll just say what the slide says, you know, that there are various ways that the particles will disperse throughout the room actually due to these turbulent eddies of air. And these are created by thermal gradient, I mean differences between wall temperatures and the internal temperature, between the floor of the room and the ceiling of the room, between open windows and doors, infiltration through closed windows and around closed windows and doors, and mechanical air supply, and just people walking around. You know, we as people have a thermal plume. We, you know, we're warm people, right? And so we cause air to rise around us. And so that's another way that air just basically stays in motion just by having people in the room. So I'm going to talk about 3 different ways that particles or infectious virus, SARS-2 included, can be removed from room air. And this combination of mechanisms is at play simultaneously. Now, I'm going to use a little math, not a lot, I'm not going to dwell on it, but I just want to show these things. There are 3 different, let's say, removal constants, and I say lambda 1, 2, and 3. I'm half Greek, so I love using Greek letters, even though I can't speak any Greek whatsoever. Anyway, so I'm going to call lambda 1 is a rate of removal via air exchange. By all these rates have a unit of fraction removed per time. Okay, and so lambda 1 describes the removal by air exchange, really air coming into and flowing out of the room. Whatever mechanism it goes out to the window, around the door, air leaves the room. And this is related to something probably everyone's heard about, air changes per hour. That's sort of related to this lambda 1 thing. So as lambda 1 increases, you get quicker removal of the virus containing particles from the air of the room. Lambda 2 is something that describes the particle's fractional removal rate via gravitational settling. And so this actually kind of speaks to the question that Marley had asked. Lambda 2 is sort of this ratio, or it's a numerator divided by a denominator. And what's in the numerator is kind of like the settling speed downward in still air, but it's divided by the height of the room. And I don't want to get into the crazy concept behind that, but basically the fractional rate at which it leaves the air of the room is going to be less than if it was settling in still air. It takes into account basically the turbulence air of the room. And the last removal mechanism I'm going to talk about is lambda 3. It talks about the virus die-off, or an activation in the air. And there are a couple of, at least one study that looked at the die-off of SARS-2 virus in air, and it found that the half time was on the order of about 1 hour. Okay, so you can shape it into a removal rate per minute. I think I have it here. And so all 3 mechanisms can act simultaneously to remove virus from the air of a room. So if I was to, at an instant in time, release virus into the air of a room and not release any more, release a bolus of virus into the air of a room, this little formula on fraction remaining at time t, like after t minutes after I removed it, this little formula says how much of the virus would remain active, infectious, in the room air. And it's a function of these 3 removal rates that I just described. And you can actually apportion how the virus gets removed from the air by these sort of fractions that I show here, which I'm not going to dwell on. But there's a way to estimate the sort of removal of the time, or really the rate at which virus is removed from the air, involving these 3 rate terms. So this is just an example. Let's say I release into the air virus, okay, of different sizes. And here's a room that had 1 air change per hour, okay? And so it's going to correspond to a certain lambda 1 term, air change per hour. And if I'm looking at a 1 micron part, and by the way, this is not still air, okay, it's air that's turbulent in the room. If I'm looking at a 1 micron particle, 44% of those particles, or the virus in those particles, are going to remain infectious after 30 minutes. If I'm looking at virus in 10 micron particles, only about 7% are going to remain infectious in room air. Why the difference? Because the bigger 10 micron particles settle a lot more quickly than do the 1 micron particles. So the particle size makes the difference in the removal of virus from the air. Depends which particle size they're in. Now, what if I increase the room air exchange rate to 6 air changes per hour? So by the way, 1 air change per hour, that top one, that's kind of like a typical value for a residence, 1 air change per hour, okay? I'm sure the residences have less and some that have more. Now, 6 air changes per hour is more typical of a hospital room. And actually, hospital rooms now with infectious disease patients under isolations could very well be operating at 12 air changes per hour. But if you're operating at 6 air changes per hour, let's look again at the 1 micron particle. After 30 minutes, only about 4% of those particles of the virus remain, versus about 44% if there were only 1 air change per hour. So the number of air changes per hour greatly affects the rate at which these virus and the particles containing virus are removed from the room air. And the 10 micron particles, well, they're going to be removed a lot more too, and now you have less than 1% remaining, okay? And there's less of an absolute difference really between the 1 micron and 10 micron particles. So a take-home message is that the more air exchange that you can affect in a room, the more quickly virus is removed from the room air. So an anecdote, personal anecdote. So I had someone come over to repair our refrigerator, and being paranoid or cautious, he was in the kitchen. I opened up all the windows to the kitchen, taking a nice cross draft, and we have a HEPA filter portable machine that we got because of all the wildfire smoke from last season, and I stuck that in the kitchen. Okay, why did I do that? Because if there was any virus coming out of that person, even though they were wearing a mask, I wanted it out of my kitchen as quickly as possible. And what did I do? I was increasing the effective air exchange rate in that kitchen. So that's, so that's a practical way that one tries to deal with particles, infectious virus in air. Okay, so now the number of virus, this is pretty important, number of virus that are emitted into room air, well, it depends on a number of things. The rate or number per time of particles emitted, or the particles that are emitted during normal exhalation or speaking and coughing. So in other words, how many particles per minute are emitted when you cough? How many particles per minute are emitted when you're speaking? This can vary. It varies between speaking, generally, the more coughing emits more particles, sneezing emits the most particles, then coughing, then singing, then speaking, then normal exhalation. But all those activities emit particles at different rates. Now, the virus titer or concentration in the respiratory tract fluid that is being emitted. Okay, so obviously that makes a big difference, and that can vary tremendously. And then, of course, in terms of total number of virus emitted, well, that depends on the duration of emission. If an infectious person is in a room for 1 minute versus 30 minutes, there's like a 30-fold difference, basically, in the number of virus that are coming out into the room air. Now, I said most particles emitted, the more particles emitted during coughing, during speaking, than during normal exhalation. And these values can vary tremendously between people. I mean, it's just there's a lot of natural variability between people. Hold on for 1 second while I take a phone call. Hi, I can't talk right now. Can you call later? Okay, bye. Okay. The concentration of SARS-2 virus, or what they call a titer, in fluid. I bet that's a spam call. Hold on. This is real life. Nothing artificial about this office. So anyway, the virus concentration in respiratory tract fluid, this is varying 9 orders of magnitude, from 100 to 10 to the 11th viral copies per milliliter. I mean, it's kind of like staggering, but there's a tremendous degree of variability in virus concentration. And it can vary also at different times of infection. It might be highest on day 2 and a lot lower on day 5. And there's usually a time course of the virus titer. It increases and then decreases. And then, of course, virus emission, because the length of a time an infected person spends in a room can also vary from setting to setting. And also the length of time a susceptible person is in a room can vary from spreading to spreading. So if given all these factors, variability between people, number of particles emitted, and what their sort of activities are, in the virus concentration that's in the room, the virus concentration of the fluid being emitted, and the length of time spent in a venue, gives a tremendous variation in virus emission between infected people. And I'm sure you've all heard the term super spreaders. Well, these are people who emit a lot of virus and therefore can infect a lot of people. So before I proceed in the next section, I'll field any questions.
Yeah, we've got a couple from actually the last one that we can jump into. I think they're definitely still relevant. Marley asked, in your opinion, is inhalation the most significant exposure route? So we'll start with that one and then jump to the next one after.
Yes, I do think it is the most significant exposure route for two reasons. That it's the easiest exposure route. I mean, just think about the droplet spray route. You have to be close to someone. Are you always close to an infected person? I mean, if someone tells you they're sick and they're coughing, if they have symptoms, right? Are you going to get close to them? Probably not, So you need, and also you need people face to face. So you need to have two people situated face to face, okay? Whereas if you just occupy the same room with someone, you are subject to the virus that disperses in the room air. It's a lot easier than the hand, that fomite hand contact the surface and surface to your hand and to your face, because there are multiple steps there. There are multiple things that have to happen before the virus, let's say, gets into your eye, because you stuck your finger in your eye. Whereas there's not multiple things that have to happen really with inhalation transmission. Yes, someone has to be in the room emitting virus. Okay, well, that can happen pretty naturally. And then secondly, you have to go into the room. Okay, well, if you're unfortunate enough to go into the same room, you don't have to do anything else. All you have to do is breathe and be present. So there are fewer steps involved. And the third thing, which, it's sort of my intuition, just consider how rapidly this virus has spread in terms of a pandemic and epidemic within the US. I mean, it's been very rapid. I just don't think that everyone has been touching the same table and causing that kind of rapidity and spread. I think the rapidity and spread itself argues for something that is transmitted by inhalation.
The other question that Marley had was, do you have any reference or know of any resources that share about food or beverages being an infection route?
Well, I don't have any references regarding SARS-2. There being an infection, being a route of infection. It's not thought that they are. I mean, even the CDC doesn't think they are. I've never seen anyone say that influenza, for example, is transmitted by respiratory tract, transmitted by food or water. I mean, the only things I know about that are transmitted by food or water are gastrointestinal pathogens like norovirus. I mean, there are certain kinds of TB that could be gotten from drinking fluid, but those are in terms of virus, the norovirus is the only thing that comes to mind. Not to say there aren't other viruses that can be transmitted by drinking or food.
I think we've got a few more questions, but why don't we keep going and then I'll kind of disperse them throughout at the next break and then at the QA.
Okay, so there have been a number of investigations that they're basically outbreak. Outbreak means that there was some point in time where people were together in one place and now a number of people were infected, so that's considered an outbreak, okay? And it's traceable back to one person, let's say. And so I just want to mention two investigations which are often cited. The first was, it was a restaurant setting in a city in China. And the deal was there were 3 tables sort of seated in a row in the sort of the back of the restaurant. And there were 3 different family clusters, one family cluster seated at each of the tables. And these people weren't intermingling with each other. Okay, my understanding, 3 family clusters. And a person with COVID-19 in one family, family A, they were seated in the middle table. That person infected 4 other family members seated at that table, and infected 3 members of family B and 2 members of family C who were seated at adjacent tables. Now there wasn't any finding that the infected family member went to those tables and sort of was face to face with anyone there. So it just seemed completely unlikely that droplet spray exposure or this hand to table to hand to mouth eye contact route would be at play in causing this person in family A to infect the members of family B and family C. So that was, one sort of outbreak investigation. And then a second was, there was this corral practice in a town in the state of Washington, and 61 people attended this practice. I think the practice lasted for on the order of a couple of hours. And then subsequently, 52 COVID-19 cases were identified in addition to the index case. They were identified either by virology or symptoms being completely compatible with COVID-19 and also the timing. So assuming 52 out of 60 people, okay, got infected there by one person, that's like 87% infection, okay, ratio. And the thing was, investigation, I'm really talking to people, the index case was situated in proximity to only a small proportion of the other crowd members. So it wasn't as if this index case went around shaking everyone's hand and hugging them, They basically had a limited amount of physical contact, okay, direct contact or close contact, if you will, with other people, but people throughout the space, okay, were infected. So this is something else that argued for inhalation transmission. There are, by the way, there are animal experiments. I don't think they're animal. The animal experiments on SARS-2 transmission do show that you can transmit infection to other cage mates in ferrets and golden hamsters. What does that mean? You have you inoculated a golden hamster who's sitting in one cage and they develop the infection. And then you have a little ways away, you have a non-infected hamsters in another cage. And then you see whether any of the non-infected hamsters got infected, and by gosh, you do. But the way it was physically set up, it was close enough that one could say, well, dust particles, from one cage somehow got transmitted over to the other cage, or maybe did the hamster cough or sneeze? I don't know if hamsters cough or sneeze, but somehow respiratory tract emissions acted as droplets and went over to the other cage. So nothing was so tightly done that you could rule out sort of this droplet transmission thing with the animals. There wasn't it's not clear to me. I heard the NAS sort of workshop, and one of the speakers was talking about an experiment where they separated hamsters by a way that would prevent the sort of droplet spray thing from happening. And it seemed to me they could limit the particle sizes that got from one cage to another, just the way that the sort of ventilation system was set up. But it wasn't clear to me, and what they found was that you could transmit infection via small particles, things were less than 4 microns. It wasn't clear to me if they were talking about influenza or SARS-2. I think they were talking about influenza. So anyway, I don't know that the animal experimentation is so clear-cut, but there certainly is evidence that if you situate animals close together in cages, I mean, not in the same cage, but in cages that are close, that you can transmit the infection. Some other direct evidence is that you can find SARS-2 virus in room air. So basically, people have gone into hospital settings, they've taken air samples, and now they analyze the air, on the air sample, they analyze it for viral RNA by using polymerase chain reaction assays. So there was sort of a recent study that came from the University of Nebraska, and they found on average about 4,000 viral RNA copies per cubic meter of air in hallway air samples. And they found 28,000 viral RNA copies per cubic meter on personal air samples that were worn by investigators who were in different hospital rooms. Now, they tried to culture some of the virus in tissue culture assays, and they reported that in some of the air samples, the virus was found to be infectious. In other words, it replicated in cells in tissue culture. Is that the same thing as causing an infection in an animal? Well, it might not be the same thing, but it shows that the virus can replicate. Then separately in a Singapore hospital, an earlier study, it was found that there was an average concentration of 1,300 RNA copies per cubic meter in 2 patient rooms. So there hasn't been a lot of air sampling that's been done, okay, looking for SARS-2 virus, but some has been done, and you can find it, okay? And actually, depending on what the quote infectious dose is, maybe these are really high quantities. Now, something about finding viral RNA copies, so has been pointed out to me, is that just because you find a virus RNA copy, okay, the genome of the virus, doesn't mean that that genome was associated with an active infectious virus particle. In fact, it's estimated that only 0.1 to 1% of all the virus RNA copies found in a PCR assay are associated with infectious virions, virion being a virus particle. So just because you found 4,000 virus RNA copies per cubic meter in the air of a hospital room doesn't mean you have 4,000 infectious virus floating around, okay? It might be 0.1% of 4,000, which is still too many for my opinion. Okay, so before I launch into the Wells-Riley risk model, which will sort of, well, this might be a good place to stop if there are any related questions.
We do have a few questions related to the UV component, deactivating viruses and UV versus filtration. Did you want to do that now or wait till the end for Q&A?
Well, I can say, yes, upper room air ultraviolet radiation is a way to inactivate any kind of virus, actually. And it was first used for trying to inactivate tuberculosis bacilli, which were in the air of a room. So do I know what the exact intensity of radiation needed to inactivate SARS virus and the length of time one needs? No, I don't know those figures, but I do know that you could use that as a method to decrease the virus concentration in room air. Can you hold on for 1 second? My cat is meowing. I want to remove it. There we go. It's always something. What was the question?
Yeah, so let me actually read the full question for you because it actually has a bit more to it. So given the virus die-off rates you show, would you agree that it doesn't really make a lot of sense to sanitize outdoor spaces? And in the outdoors, if you have the UV component of sunlight deactivating the virus, in the outdoors, because you have the UV component deactivating the virus. And then the other part was, would sanitizing university campus classrooms or hallways make sense? And that's from Ilse.
Well, I mean, we're talking about, I don't know what sanitizing means. I mean, in terms of what the method being thought of is. I mean, in terms of like wiping surfaces, you know, I mean, who can be against wiping surfaces and keeping them clean? I just don't think that there's a lot of, transmission via this hand contact route. So I don't think that it's going to have a great effect on reducing the risk of infection. I think that focusing on actually, you can call it disinfecting air or getting the virus out of air is a better route to go, as well as maintaining physical distance between people. Because again, the closer you are to someone, the more subject you are to breathing a higher concentration in air, and then also the combination of wearing masks to reduce emission and also to reduce inhalation of virus. So to me, sanitizing something in terms of surfaces, to me, does not seem so as important as trying to increase the removal of virus from air. Now, in terms of going back to UV light, you know, in large spaces, you know, like if there was a large classroom setting, it's hard to bring in enough new air or use multiple portable HEPA filter machines throughout the space to actually greatly increase the amount of air exchange in the room. In that kind of setting, it might actually be more efficacious to use upper room air ultraviolet radiation at the right, you know, wavelength, which is like that 250 nanometers or 253, 254, because that might just be simpler. You know, the thing about UV is that I think that wavelength, it's not harmless, so you have to make sure that you have to arrange the lighting in such a way that you're not reflecting too much radiation down into the zone of occupancy where people are. And also you have to maintain the cleanliness of the lamps because, you know, dust is going to settle on them and it's going to cut down their intensity. So you have to have people running around who are going to clean these things and keep them working properly. But I think in a large space, it's hard to increase ventilation substantially. And in that kind of a space, I would say in an academic setting, which I no longer am in personally, I would say that in a large space, upper room air irradiation would be probably better than more ventilation, which would be hard to achieve, but wearing of masks or respirators and spacing people would be a very useful thing to do, you know, limiting the number of people. So I don't know if I sidestepped that question or answered it.
Yeah, I think you did, but just a really quick clarification, which relates to another one. So then in that case, does it make sense to install UV lamps that could be turned on at night on university campuses? In your opinion?
Can't hurt, you know, I mean, it really depends on what kind of, is the ventilation system going to keep running or are they going to turn it off? If they're going to turn it off, in other words, if the class ends at 5 p.m., okay, and everyone leaves and they turn off the ventilation system, now they're going to, the only air exchange is by infiltration, exfiltration out of the room, which will probably be at a pretty low rate. But most particles will settle out of the room air. But now, will they be resuspended when you come back in? I don't really think so. And what's the die-off rate on surfaces now? Well, though it's overnight, there'll probably still be a lot of viable virus left on surfaces. So, I mean, stuff to settle on the surface, it depends what you're irradiating. If you're irradiating everything in the room, that would be one thing. If you're just irradiating the upper room air, that would be another thing. And I don't think the idea is that you would bathe the room, all surfaces in UV light and sort of sanitize everything in the room. I mean, you could do that. That would be one way to do it. But you know, within half an hour of the next day's class coming in, that all goes out the window, right? Because now you have people who are potentially infectious, sort of dirtying the room up again for the rest of the day. Wasn't a very clear answer. What would I do? I probably would not use UV irradiation overnight. I'd probably leave. I'd probably let the air exchange system run for some hours and then turn it off. You know, so if everyone leaves at 5, maybe I'd leave it run for to achieve maybe 12 air changes per hour and then turn it off, or 12 air changes and then turn it off, and that might take a couple 3 hours.
Thanks. We've got a few more questions, but why don't we keep going, because
Okay.
I think some of them might be addressed in some of the later slides.
Okay, so so at present, aerosol scientists are using something called the Wells-Riley risk model to think about SARS-2 infection risk upon inhalation. Now, this was a model that was originally applied to pulmonary tuberculosis, which is another disease that's transmitted by inhalation. And this model uses the idea of a quantum of infection. And a quantum is that number of pathogens that constitutes an infectious dose. And it's not specified how many pathogens that is. It's just that the idea there is a number that constitutes an infectious dose. And this goes back to what I mentioned previously, the idea that there's a threshold number. So a quantum might be considered a threshold. There's some threshold number of pathogens, in this case SARS-2 virus, that if you receive that number, you will be infected with certainty. And if you receive one less than that number, you won't be infected with certainty. And I don't think that that is a particularly realistic way to think about the likelihood of infection. I think it's more realistic to think about it in terms of you inhale a certain concentration of virus and you receive a certain dose, and it imparts a certain probability of being infected. But that said, there's not really enough information about SARS-2 virus to start trying to tease out what this probability per dose is, okay? The Wells-Riley model also assumes that, well, it assumes everyone is infected with certainty, but it assumes that everyone is as susceptible as everyone else. In other words, the same quantum dose, the same number of virus that infects person A with certainty is also going to infect person B and C and D and E and so forth with certainty. So it doesn't account for any kind of variability, at least, you know, explicitly, in susceptibility to infection. Now, as usually posed, the model assumes that the air in a room is perfectly well mixed. What does that mean? That the pathogen concentration is the same at 2 feet from an infectious person versus 20 feet away. In reality, that's not true because exposure intensity is higher close to the source of emission than further away. You could tweak the model and take into account spatial variability. So that's not really any fatal shortcoming, although it's not typically factored into this model. The model, as usually posed, it assumes that the concentration of the infectious agent in room air is at steady state. What does that mean? The concentration is not changing over time, which means that the rate of emission of the pathogen into room air is matched perfectly by the rate of removal of the virus or the pathogen from room air. And generally, when when the room's clean and now emission starts, that's not steady state. The concentration builds up over time and reaches this sort of steady state value. And how quickly it does that depends upon largely the air exchange rate in the room. So time can be factored into this model. It's not usually. The model as posed also assumes that all the inhaled virus or pathogen deposits in the respiratory tract. And it doesn't, because actually we inhale in particles and a portion of them deposit and the rest are breathed out. I mean, our respiratory tract is not a perfect filter that removes all particles. And also it doesn't take into account that the site of deposition may affect the risk of infection, okay, but it may. So this is some math, okay? So this top equation, this is the Wells-Riley risk model. It says risk, or the probability of infection, is equal to 1 minus, and then E is the base of the natural logarithm, and then dose is this thing we're going to compute in the next line. So if you tell me what the dose is in terms of quanta, how many quanta are inhaled, this equation says, well, here is the risk of likelihood of infection. And the dose, well, this is kind of logically constructed. It looks kind of, hard to comprehend. But you see that E is the emission rate in terms of quanta per hour. How many quanta per hour are being emitted into the room air? And the denominator is sort of, that involves those lambda terms in the room volume. This is basically an effective air exchange in the room, or airflow in the room. If you multiply the units out, you would find it has the units of cubic meter per hour. And when you divide E, which is quanta per hour, by this cubic meters per hour, you get a unit of quanta per cubic meter. It's basically, this ratio is the concentration of the quanta, as expressed as quanta in room air. So emission rate, removal rate in the denominator. So here's you have the concentration, and logically, if you want to compute a dose, you multiply that by the breathing rate, okay, how much cubic meter of air you inhale per time, and then you multiply that by the total time of exposure, and you get this quanta property, okay, the number of quanta. Now, something to point out, this dose term does not need to be an integer value, which is kind of weird, right? Because how can you have a dose of virus that's not an integer? Well, just mathematically, it doesn't need to be, okay? The probability structure of this model sort of takes into account that you don't have to have integer values for dose. But anyway, so this dose is related to emission rate, all these removal rate terms, the breathing rate, and the time of exposure. And actually, if you look at this concentration term, E divided by all those other things, it kind of gives you a clue as to how you would decrease risk by decreasing the concentration in air. I mean, what would decrease E, the quanta emission rate? By wearing some kind of face covering. The infected person wearing a face covering, that would decrease E. There would be less getting out. How would you increase the removal rate from room air? Well, see that lambda 1 term? Well, that relates to the ventilation rate of the room. So you can increase ventilation. The lambda 2 term you can't change. That really relates to particle settling. And the lambda 3 term, the virus die-off, well, you can increase that by UV irradiation. So that's a way you can increase that. But it gives you a kind of a flavor or strategy of how one would decrease the concentration in room air. You can't really increase your breathing rate. Maybe you could breathe every other breath, I don't know. And then time, well, you spend less time in an environment. I know when I go grocery shopping, I don't go linger. I know what I want, buy it, and get the hell out. Okay, so this Wells-Riley risk model was applied to that COVID-19 outbreak among those Skagit Valley, State of Washington Chorale members, okay? And without going into the details of what they did, it was estimated that the index case, the person who was infected, beginning, had an emission rate of 970 quanta per hour, okay? But because there was uncertainty in the true values of all the other input factors that go in, they put these 95% uncertainty bounds on the true emission rate, and it was between 400 and 2,000 quanta per hour. So this is the only study I know of that has tried to sort of quantify the emission rate of virus in terms, the rate of emission in terms of quanta per hour. There have been studies that have sampled for viral RNA copies in room air, but that wasn't getting at the emission rate per se. So this is sort of an emission rate term. And I should note that in this case with singing, and of course, if you sing, you produce more respiratory tract particle emissions than if you're just sort of breathing. So you could say this is really, it doesn't represent someone who just normally exhaling, okay, and what their emission rate is. So a question, what would the Wells-Riley risk model predict for a more typical scenario? Well, it depends on what you think is typical. So I'll pose a scenario. So I'm going to say, well, there are 200 viral RNA copies per cubic meter of room air, and that's about 1/10 the findings in hospital rooms. Okay, so hospital rooms containing sick people, you're going to have a lot of virus, and maybe you have 1/10 of that where people aren't obviously sick or something like that. It could be less. I don't know. I pose it this way: only 0.1% of viral RNA copies are actually associated with infectious virus. Okay, I picked 0.1%, it doesn't have to be true. So what that means is that there are 2 infectious virus per cubic meter of air in my hypothetical settling. Now, what if a quantum is 10 active virus? I don't know what it is, okay? I just made up a number, 10 active virus. So that means the room concentration in this room is what did I say, 0.2 quanta per cubic meter, okay? The breathing rate, the default assumption is 1 cubic meter per hour. So if you spend 1 hour in this room, the expected inhaled dose is 0.2 quanta. It's not an integer value, but it doesn't need to be. You stick that into that Wells-Riley risk equation, and it says the risk of infection is 18%. Now, does this have a semblance to reality? Well, it really depends upon the semblance to reality of the input factors that I pose in this hypothetical scenario. The breathing rate, I'd say that's realistic. Spending 1 hour in a room is realistic. You know, maybe the room air exchange rate and volumes are realistic, but I don't know about the viral RNA copies per cubic meter of room air, and I don't know about the percent of RNA copies associated with infectious virus. All right, so I'm going to leap into ways to reduce inhalation exposure. But let me just do this because I've really covered most of this already. So I said social distancing, that's indoors and outdoors. I mean, outdoors things, the viruses, anyone emitting virus outdoors, when you're 6 feet away, it'll be a lot more dilute than if it is if you're indoors 6 feet away, because there's ambient wind, and ambient wind serves to disperse things more quickly, and then you kind of indoor air stuff unless you have a fan sort of directed at you. So keeping a distance indoors and outdoors is important. Now in indoor spaces, I personally would avoid crowded venues where you do not need to be. I do not need to be in a bar. I do not need to be in a movie theater. There are many other places I don't go because I don't need to be there. I'm sure owners of bars and movie theaters would write me and complain, but I'm telling you that I wouldn't be in those places. And what's that going to do? Where you are is going to decrease the emission rate to 0. Because you're going to be at home and the emission rate is going to be 0. It's not going to be greater than 0 because you're not in a bar. Okay, you don't know who's in the bar with you. There could be someone who's infectious emitting stuff into room air. Now, in indoor spaces, we can increase the air exchange rate of the space by increasing the mechanical supply air to the space, or you can, if there are operable windows, you open the windows, like I did in my kitchen, or if there are doors, you keep the doors open. And that's what people do in stores now. They keep the doors open and they open windows. And that's a way to increase the ventilation without, you know, upping the mechanical supply system fan. In indoor workplaces, where you have a building that has, a mechanical air supply system, well, I would not recirculate. Most buildings work with recirculated air. You're going to recirculate a certain portion of the air in the building to save on energy. It might be 80% of the air. You'll take it from rooms, and then you'll pass it maybe through another filter, take out big particles, and shove it back into the general air supply, making up 20% of the air with outdoor air. And the thing is, when you recirculate the air in the building, if there's any virus in the air in the room, now that you're going to recirculate that. And so it would be safer to not recirculate any air. So you have a one-pass system. And in the summer times, in temperate weather, that works well because you don't have to heat the air. And if it's temperate, you don't have to cool it. But in the winter, that might be a problem, okay? Indoor spaces, well, if it was a smaller room, you could buy portable HEPA filter machines. I mean, a portable HEPA filter machine basically takes room air, sucks it in at some point, passes it through a HEPA filter, which removes small particles. Really, almost all the particles that contain virus will be removed, and then it puts out it blows the filtered air back into the room. So that's really a good way to increase the effective air exchange rate in the room. And if you had the means, you could buy several HEPA filter machines and put them in different places throughout the room. And then, of course, we mentioned ultraviolet radiation. In a workplace, in a room, you can use upper room air ultraviolet radiation. If you wanted to recirculate air in your building supply, then there are ways to put ultraviolet radiation inside a supply air duct or at some point in the air handling system such that you pass the supply air through a high intensity UV field for a sufficient time that it inactivates any virus that's present. It's probably more expensive than other ways of doing it. Maybe not, I haven't really costed it out. All right, well now I want to get into face coverings. This is sort of the last part of my talk, and I would take any questions before I do.
Yeah, so related to that, Mark, I guess there are two. One's from Tara Pearson, and they're asking whether around the HEPA filters, are there any recommendations around or resources that you're aware of that report out on different models that effectively reduce that virus or mitigate the concentrations in the room?
So if it's a HEPA filter machine, the HEPA filter should be tested against the same standard. And so the filter should not, as long as you're buying it from a reputable company, the filter should work from company A to company B the same. What might differ is the amount of air that is being moved through the HEPA filter by the machine. So you can buy a machine that maybe moves, making these numbers up, maybe it moves 50 cubic feet per minute of air through the HEPA filter, where there's another machine that moves 200 cubic feet per minute of air through the filter. Or there's some machines that will allow you to move different amounts of air. But the more air you can move through the HEPA filter per unit time, the greater the effect is of reducing the particle and virus concentration in the air of the room. So I would go for a machine, and you can think about, usually a manufacturer will tell you how many CFM of air, okay, is being moved by the machine. So you can think about, well, what room am I sticking this into, okay, and how many effective air exchanges is this going to provide for my room? So if I had a room of 100 cubic meters, see, everything's in CFM, and I have to change it back into between cubic meters and CFM. But let's say I have a 100 cubic meter room, and I have a HEPA filter machine that can move 100 cubic meters per hour of air through the HEPA filter machine. Well, that affected 1 air change per hour. If I had a different HEPA filter machine that could move 300 cubic meters per hour, well, that will affect 3 air changes per hour. What would I do? I'd want to buy the bigger machine that moves more air because you're going to have a greater effective air exchange. So that's how I would think about that. Of course, now you have the bigger machine might be noisier. There you go, and I'd probably look at consumer reports for HEPA filter machines and see what's recommended in terms of reliability. But in terms of the effective air exchange, the way to think about it is what's the volume of the space I'm interested in, where I'm interested in putting it, and how much air does this machine move? And I'd like to achieve more air exchange than less.
Thanks, Mark. There are more questions, but I think being mindful of time, I think it's probably right now more important to get through the next section.
All right, so this is the last really segment. So there are numerous types of face coverings being worn presently, and they all relate to COVID-19. You know, bandanas, gaiters, cloth masks, medical procedure masks, FDA-approved surgical masks, NIOSH-approved respirators. An N95 filtering face piece respirator is a NIOSH-approved respirator, and then there are counterfeit N95 filtering face piece respirators. Okay, that they usually come from China. They're called KN95s. That's the K is sort of a Chinese designation for the way that they test their respirators. If they were really tested according to the Chinese standard, the filter would be as effective as the ones that are tested in the US, but they're counterfeit. Many are counterfeit, not all, but many are counterfeit. And so they don't have the same filter efficiency. These devices, all these devices will provide some degree of a reduction in virus emission by the wearer, if the wearer is emitting virus in the first place, and they will provide some degree of protection for the wearer. They are not all equal in effectiveness for either purpose. And by the way, FDA, Food and Drug Administration, NIOSH, National Institute for Occupational Safety and Health. NIOSH is an agency within the Centers for Disease Control that's related to research on workplace hazards, and they have a regulatory mandate responsibility for testing and certifying all respirators used in US workplaces. And I'll talk about the N95 and what that is, but that's an N95 respirator is one of those kinds of respirators. So my only graphic of respirators, my kitchen table with a very colorful tablecloth, I might add. But anyway, on the top, you see one kind of N95 filtering face piece respirator. This is not an endorsement. This is made by 3M Company. And this has a cup shape. Others have really more of a flat shape when they lie on a table. And these NIOSH-approved respirators, they will have a label on them that gives you a NIOSH certification number. You know, I can't really see it on this, but it's either on the respirator or on the box that the respirator comes in, okay? So if you want to know if a respirator is NIOSH certified, and tested and certified by NIOSH, someplace on the respirator or on the container of the respirator, there will be a NIOSH testing and certification number. And this is a NIOSH certified respirator. The bottom is a cloth mask. These are not tested by NIOSH, they're tested by nobody, okay? You make them if you want to. You buy them online, you know, you get them from friends. It's a cloth mask. And what you can see though, it has ear loops, okay? See the top one, the yellow bands, these yellow bands go around the head, on the lower part of the head and the upper part of the head. The ear loop respirators go around your ears. And in general, these N95 respirators with the two headbands are going to make a snugger fit on your face. And the snugger the fit is on your face, the less leakage is going to occur around the perimeter of that facial covering. So there's a difference, I'll talk about it, but you know, things can get into a mask through two routes. They can get in through the filter medium itself, and for that respirator on the top, the whole mask really is the filter medium. And for the mask on the bottom there, the cloth is the filter medium. And they can get in around leaks in the perimeter of the mask. So for the mask on top, you know, usually you get a lot of leak points around the nose bridge or maybe around the chin. And for the mask, and you could get some around the sides, but for the mask on the bottom, depends how it fits your face. What I see personally when people wear cloth masks is that along the sides, along the cheek area, you have these visible gaps. A visible gap means that when you inhale air, the air is going to come in through the sides. I mean, a lot of it's going to come in through the filter itself, material, but a lot of air will come in through the sides, so these leak points. So you can't just look at filter efficiency, you have to consider the overall penetration, if you will, of particles into these respirators. Now, I just went over this really. There are two ways that particles get into a respirator. They can penetrate through the filter medium, or they can basically have unfiltered air penetrating around the gaps in the perimeter of the face piece. Now, an N95 filtering face piece respirator filter is going to be more efficient than a surgical mask filter, which in turn will be more efficient than a procedure mask, will in turn be more efficient than a cloth mask. So the N95 filtering face piece respirator of all these kinds of respirator, of all these facial coverings is the best in terms of filter efficiency. But unfiltered air can also enter around gaps in the perimeter of the face piece. And so here's my ranking of perimeter leakage. For the N95 filtering face piece respirator, it's less than for the surgical mask, which is less than for the procedure mask, which is less than for the cloth mask. So just looking at those lines, which ones do you think, which respirator do you think would be the best? The one that has the highest filter efficiency and that allows the least amount of perimeter leakage. That would be the NIOSH approved N95 filtering face piece respirator. It is the best choice among all those facial coverings. The problem is that they are scarce because they are the most effective devices, and there is a desire, and because they are the most effective, there is a desire to reserve their use for the most highly exposed persons, basically frontline healthcare workers who are treating COVID-19 patients. So you can't buy them. I mean, it's hard. You go online and you need to be really wary about what people are selling online. And you go to the store, you can't buy them. You go to a safety supply house, they're out. So they're very hard to come by. There are other NIOSH approved respirators that really might not be so scarce. And what do I mean by that? Well, you've probably seen a person who's spray painting sometime and they're wearing kind of a rubber type face piece with screw-in cartridges or filters. Well, these are called the elastomeric face pieces. They're kinds that fit from the bridge of the nose under the chin. These are called half-mask respirators. And you can equip them with different kinds of filters, including N95 filters or things that are even more efficient called N99 or N100. So I think that it's possible to still buy online even, or at a store, one of these elastomeric face pieces. And my personal opinion is that I think they allow less perimeter leakage than does the filtering face piece respirator because they tend to make a more snug fit on the face. Now there's a different kind of respirator. These can also be purchased NIOSH approved that are called power air purifying respirators. And what they do is they take air from around you and they suck it through a HEPA filter and then blow it into a head covering. Maybe it might be a hood or it might be a tightly fitting face piece. And so it tries to maintain a positive air pressure within the face piece. Not perfect. And it allows less inward air leakage than does one of these elastomeric face pieces, or less leakage than a filtering face piece respirator, because these elastomeric face pieces operate on the principle that when you inhale, you develop a negative pressure inside the face piece, which causes air to come through the filter. But if there are any leak points around the respirator perimeter, well, the air wants to go through those too. And the powered air purifying respirators try to maintain more positive pressure in the face piece. So if there are any leak points around the perimeter, the air goes out and not in. Now, what does N95 really mean? So let me try and explain it. So NIOSH tests N-series filters using 0.3 micron sodium chloride particles. And I believe the N comes from the sodium chloride. And if the particle, and what they have a system that counts the particles that come through. They can count the particles in the challenge aerosol upstream of the filter, and they can count the particles downstream of the filter. They're sucking the air through a filter. And if the particle penetration is less than 5%, the filter qualifies as N95, which means it's at least 95% efficient. Now, it doesn't mean that the filter is actually allowing the penetration of 5% of particles. Why? Because 0.3 microns is considered the most penetrating size for a filter. In other words, if the N95 has better efficiency in removing smaller particles and larger particles. So it might be close to 100% efficient for removing particles that are 2 microns. And it might be close to 100% efficient for removing particles that are 0.05 microns. So this 0.3 microns is considered the most penetrating size, the least efficient. So the great majority of the virus emitted from the respiratory tract is in particles that are smaller or larger than 0.3 microns. So therefore, the overall particle penetration through the filter is less than 5%. It's likely a lot less than 1%. And therefore, when we're just with the filter, a lot less than 1% of the virus in the air is going to pass through that filter. So you might think that, well, why don't they consider this like 99% efficient filter? Because not all the air goes through the filter. Unfiltered air can enter the respirator through perimeter leak points, and that's often around the nose bridge area and the chin. So there's something in the occupational health world called a fit test. You sort of test how much, whether there's too much air leakage, if you will, around the perimeter of the face piece. And if a person passes one of these fit tests, it is assumed that the perimeter leakage can contribute as much as 10% of all the air that you inspire. What does that mean? 90% of the air you inspire comes through the filter itself, and 10% comes through these leak points. The actual percent leakage through these leak points, when worn during normal activities, can be higher or lower. This 10% thing is not some fixed value. So what about other kinds of devices? Well, Food and Drug Administration approved surgical masks tend to have good filtration properties, but most are not designed to fit snugly on the face, and therefore they permit a good deal of perimeter leakage. Very limited testing has been done on the filtration efficiency of cloth masks as constructed, and also their perimeter leakage tends to be substantial. So I'm going to give you my ballpark estimates. You know, this is basically my sense of the literature, and there's lots of studies in the literature if you wanted to go look for them, of the overall penetration of aerosol particles carrying virus, given different face coverings. And this is filter penetration plus perimeter leakage. A fit-tested N95 filtering face piece respirator would allow 5 to 15% total inward leakage of virus particles. An N95 filtering face piece respirator that wasn't fit-tested, and no one in the general public is running around with a fit-tested N95 filtering face piece respirator, I would say 15% to 25% leakage. An FDA surgical mask, about 25% leakage, a cloth mask, 50%. So which one would I choose if I had my druthers? I'd pick the N95 filtering face piece respirator and get it fit tested, because it's allowing the least amount of total inward leakage of these small particles that would be carrying virus. All right, protection for others. Well, for the general public, face coverings are recommended.
Sorry to interrupt you, Mark. I'm just noting that we're coming up on time now. Do you want to keep going for a little bit longer? We can stay on longer.
Okay.
Also, as a reminder to guests, we're going to be posting this online within the next 2 weeks as well.
Okay. So for the general public, face coverings are recommended because they do reduce virus emission of particles containing virus. These recommendations are often made oblivious to the additional benefit for the wearer. Anyway, they do decrease emission, but few studies have quantified their effectiveness in that regard. And the usual focus has been on filter efficiency, but we really can't ignore the amount of outward leakage around the face piece perimeter. I'll just mention that there have been a couple of studies that have quantified emission reduction from surgical masks, and they were on the order of about 70–75%. So, you know, it's really pretty good, actually. And these are the slides that talk about that. I must say that something very important about the efficacy of the surgical masks for preventing emission and infection is the compliance of people wearing these things. You know, the compliance of the infected person wearing the mask. And there's nothing, so in household studies that are done where you give the infected person, let's say with influenza, a surgical mask and ask them to wear it, it's found that there's really marginal effectiveness in preventing other household members from being infected. But in these studies, what's really unknown and not quantified is the degree of compliance of the person who's actually who would wear the surgical mask. So there have been there's been lots of modeling recently by people, epidemiological modeling, and the argument being made is that, well, you know, the widespread use of face coverings would substantially reduce infection and mortality incidence, and I agree. But, you know, and why? Because, you know, if an infectious person wore a mask and reduced the emission by 2/3, let's say, you know, so like 67% reduction, and if people wore masks that similarly reduced inhalation intensity by 67%, okay, which is not great, maybe standalone, the overall reduction in population exposure to the virus would be about 90%, and that's pretty significant. The problem is achieving compliance with wearing masks, both by people who are infectious and by people who are not infectious. So, you know, I don't have a solution to the problem of compliance. So these last slides really are they're just summary points of what I talked about in the last, hour and a half. And then right at the end, there are these references that for studies that I was citing.
Thanks, Mark. So we actually have a fair number of questions. So one option is, since we're at time, what I can do is I'm going to go ahead and read some closing remarks, and then those of you who had questions, assuming you're okay with this, Mark, we can sort of stay a little bit after and address those so that they're in the recording. Sure. Okay, great. Let me. So I just wanted to, for those of you that attended, I want to thank you again for joining us for the first talk in our fall series. We're going to be posting this recording of tonight's event later, hopefully in the next 2 weeks. Please visit the Schott Center website for more information on upcoming events. Just a reminder to join us next week, or join us for our next talk on September 17th at 7 p.m. Pacific. Omar Tesdil, an assistant professor of geography at Birzeit University, will be speaking. His research focuses on agroecological and landscape change in the Middle East and North America, and he will be speaking to us about open science methods for building agroecosystems. Okay. Oh, Mark disappeared. Where'd he go?
No, I'm back.
Oh, okay. Okay. So let me, we'll go ahead and shift into the Q&A, and let me see. I'll just sort of go down the list here. So Byron, who was asking, so you talked a bit about all of the modeling efforts that are going into thinking about spread. He's wondering, you know, given all of these assumptions, how far out time-wise are we from deciphering with greater certainty some of these parameter estimates in order to improve risk models?
You mean the emission rate, for example?
Yeah, route of exposure and dose dependence specifically, it says.
I don't know how close we are. I mean, the emission rate, probably that would be closer. You can think of an experiment whereby you would have sick people basically exhaling or coughing into some apparatus that would collect all the particles, and then you would assay how much SARS-2 virus is there. And if you could get sick people to do that, then you could probably get at the emission rate, because you could say, well, they're breathing into this apparatus for 15 minutes, and how many virus RNA copies are they putting out, or they're coughing every minute into this apparatus, how many virus RNA copies are they putting out? And so in that way, if you had a series of people who were infectious, who did that, you could get at the emission rate. Now, I don't really know how easy that would be to arrange, okay? But that would be one way of doing it. The other way would be to say, well, okay, the person is in this room, they put the person in the room now, and we're gonna sample the room air episodically for virus RNA copies, and we know what the room air exchange rate is, and we'll measure the RNA copies in the room air over time, and we'll titrate back out what the emission rate was of particles of the viral RNA copies emitted into room air, taking into account things that settled out in the air exchange rate in the room. So that's one way of doing it. The infectious dose work, well, you know, that would be done in animals. I don't know how close it is to being done. I mean, it's probably being done right now in, like, you know, small mammals. It's probably not being done in poor rhesus monkeys just because they're expensive to work with. And so how transferable information is on infectious dose in mice to people, I can't say. Virologists would probably have a better handle on that. But that kind of work's probably being done now in terms of small mammals. So emission rate, infectivity, I would say that. You know, in terms of variability based on genetic factors, that's a real, an age, and it's a real gamish. You know, there's been work done with mice. This is actually, it was a guy who talked in the NAS workshop about genetic differences between mice and what the difference in infectivity was between strains of mice. And they had mice of the same strains. They had a really fat mouse, okay, and a thin mouse. They fattened up the mouse because they would eat. It was like a balloon. And what they found is that that mouse was more susceptible to the virus than was the thin mouse, which sort of was consistent with the fact that one of the risk factors, I think, for COVID-19 severity is obesity.
Tesfa Jakob asks, can you speak a bit about UV-based versus filtration-based disinfection approaches for HVAC?
not intelligently. I mean, I don't know how feasible it is to basically install UV light in a supply air system, in an HVAC system. It is feasible to install HEPA filters in a system. You'd probably have to then up the so your fan so that you can draw more air, because now you have more resistance to airflow through a HEPA filter. And which one is more, you know, economically feasible and technologically feasible, I can't really speak to.
Andrew Slocum asks.
Andrew Slocum, okay.
Yeah, another TA, another former TA. Any discussion on masks? Early on, we talked about masks being a bad idea because of concentration of particles, false sense of security. Now you're basically considered evil if you're not wearing a mask.
Well, I think the early messaging on masks was stupid. Okay, stupid and ill-informed. Why do I say that? Because I remember the early messaging on masks was, well, the public shouldn't be wearing masks, and they're not needed, and don't wear any. And why was that? Because there was a concern. One, because the idea was that social distancing would take care of it. But two, they didn't want people wearing masks that would be taken away from healthcare workers who were basically being the most highly exposed. And, you know, and the idea was that, you know, surgical masks are going to be great too. They're just as effective as N95 filter replacement respirators, which they're not. But you have to make these available to healthcare workers. So let's not encourage the public to wear these kind of masks, you know, because we want to reserve them for healthcare workers. And part of the pitch for that was to downplay their general effectiveness for the general public, which was, you know, a stupid message, because really it's not true. I mean, they reduce virus emission, and they do offer a modicum of protection for the person who's wearing it. So now it's changed to, yes, wear masks all the time when you're out in public, because you don't know if you're infected, and you want to reduce virus emission, which is true. And what they don't say is, and wear some kind of mask to protect yourself in public, because again, the people who in public health who generally advocate mask use don't understand what these masks do in terms of exposure reduction. I mean, they're just, I come out of industrial hygiene, which sort of focuses on workplace exposure, and the use of respirators is always a big part of industrial hygiene. So I know about respirators, but I don't think that most people who come out of public health, especially epidemiologists, know a damn thing about respirators, okay, I mean, to put it mildly. So they don't understand, you know, really all the ins and outs of it. And not to say I'm a genius, but I know better the ins and outs of those. So anyway, I think the messaging initially was for the right reason, but the wrong messaging. And I think that there's still a misunderstanding of the nature of the nature of efficacy. You know, I still see it written that an N95 respirator will reduce emission by 95%, because 5% of the particles will get through the filter. I mean, it's completely oblivious, you know, to what the filter does and what face perimeter leakage is. Does that answer the question? By the way, the mask doesn't concentrate anything. Now, it is true, by the way, that wearing a face covering, there's a certain kind of dead space between that physical mask and your face, right? And so they call that a dead space. And for a filtering face-piece respirator, it might be in the order of 100 milliliters in volume. And when you exhale air, I'm not talking about particle concentrations, you're exhaling carbon dioxide, because that's what we, you know, give off due to our normal respiration metabolism. And so you have about maybe 40,000 parts per million of carbon dioxide coming out in your exhaled breath, and that's going to be captured. All the 100 milliliters of air inside that face piece is basically going to be exhaled air. And now you're going to inspire. So you're basically going to re-inspire, you know, this elevated carbon dioxide concentration. But, you know, if you're at sort of normal like work activities and stuff, you'll probably be inhaling about 1,000 milliliters altogether, maybe more, maybe less. And so you're going to have a far reduced concentration of carbon dioxide that's inhaled. Maybe it'll be around 4,000 part per million. So is that a dangerous concentration? I don't think so. You know, if you look at the millions of people in Southeast Asian countries and in Korea and Japan China, who just regularly wear cloth masks due to air pollution, okay? I mean, if there was and the millions of US workers over decades who have used respirators, okay? If there was a problem with wearing these respirators, okay, because you're inhaling too much carbon dioxide, I think we would have seen it by now, okay? So I don't really give any credit whatsoever to arguments that wearing the mask is dangerous. It is true that for some people it can have extra breathing resistance. That might be, if they have really severe problems, you know, sort of cardiovascular pulmonary problems, it could push them over the edge. But, you know, most people don't have those, especially young people on college campuses, where you are.
Thanks, Mark. Tina Hong is asking, what's your opinion regarding the safety of airplane travel?
I personally wouldn't get on an airplane. Yeah, airplanes in general these days have pretty good ventilation in the sense that they move a lot of air through the cabin and they recirculate it, but it's HEPA filtered air. And the way they have the, can you hear my cat meowing? Because if not, I won't get up. Okay, forget it.
You can, it's not that bad though.
It's a natural ecosystem. So the way ventilation systems are set up on planes is that the row you're in, the air comes in through the top, right, from the ceiling level, and then it kind of like is taken off at the bottom. And so the air is kind of meant to circulate within your, if you're in like a 3-seat aisle, 3-seat thing, the air is meant to circulate within your 3-seat area. And it's not intended to exchange with the rows in front of you, okay? But on top of that, you have this overall advective flow, usually from the front of the cabin to the back of the cabin. So you would figure that you don't have widespread contamination of the air on an airplane. The fact is like the people, you know, so yeah, you try and recirculate air within your same row. So maybe if you're sitting next to someone, you're not really too protected by the airflow arrangement, but the air is not going to stay in your row. There's going to be some air exchange with this row in front of you and the row in back because air is turbulent, and so it's going to move in all directions. And so what you find on sort of on airplane studies when you have outbreaks is that it's the people within the first couple of rows of the index case who are the ones who got infected, which makes sense because they're the closest people to the infectious source. But you don't know who you're sitting next to on an airplane. I mean, that's just the reality. You don't know who's sitting next to an airplane. I understand these days that airplanes are really crowded up because of fewer flights and they want to stick more people on the flight that's going. And so I think that, is the airline tracking the infection experience of its passengers? Are they calling them up and doing, saying, oh, how are you now? You took our flight a week ago, how are you feeling? No, so it's an unknown. So I would say I wouldn't go on an airplane if I didn't have to. Now the airline industry will be after me, bar owners, movie theater owners. Don't record this, no.
It's too late, Mark. We can bleep it out if you want. Jana asks, it has been difficult to find case studies from real-world larger space installations to support the effectiveness of upper air UV, that is outside a lab setting. The virus particles are small and complex. The UV light has to be of a certain quality and lamps have to be kept very clean, as you mentioned. It has to hit all parts of the particle to kill all the virus. And that requires a certain residence time within the UV lit space in the ducting or room, which is very difficult to control with conventional HVAC. In addition, there are safety concerns of UV exposures to human skin and eyes, so proper installation is crucial for these reasons too. Do you know of any real world case studies that look at these operational components and results?
I don't. On the other hand, I haven't really researched that topic. I think the probably where I would go look is the tuberculosis literature, because the idea of upper room air ultraviolet radiation really was popularized by the idea of using it for tuberculosis control. So if there are really real world studies where they've tried to look at reduction in infection incidence, okay, due to the use of upper room air UV, it would be in that literature. I know that this is back in the 90s, early 90s, when there was a resurgence of tuberculosis in the US, coincided with the HIV epidemic and really more multi-drug resistant TB strains. There was a proposal for using UV, upper room air UV in homeless shelters, as a way to basically decrease incidence among people who were staying in those shelters. So, did anyone do a prospective study saying, well, here's what the incidence is now of people stay in shelters versus here what it is after we stuck in the UV light? I don't know, but that's the literature I would look in first.
Cool. Ilse is asking, you mentioned the problem of compliance for wide compliance being an issue for masks. Should we also consider the issue of risk compensation behavior, meaning people reduce physical distance or other measures by feeling safer with the mask? Are there effectiveness studies that account for this? If there are none, would this limit significantly the validity or efficacy of studies?
Well, I don't know of such studies, so that's the first thing. This speaks to the issue of the false sense of security. Okay, so I think that to counter the false sense of security, people need to understand the limits of the efficacy of the mask. If you're telling, if you tell someone, a cloth mask is good, it's going to help, it's going to reduce emission, and it will reduce your exposure by 50%. Are they going to think, is that going to register with them? I don't know how you give them that message, but if I was told, hey, that thing you're wearing, that's going to reduce your exposure intensity by 50%. Am I going to think, geez, I'm really safe, so I can just throw caution to the wind, and sort of run around? Or, wow, this thing, it's helpful, but, it's not really doing a job for me, and so I better keep my distance. I don't know. I don't know. I can't say how most people think because I've decided that I'm not like most people when it comes to this question.
Marley asks, I think there has been a grave missed opportunity for public health education about what masks/face coverings actually do, and that physical distancing is actually more effective based on the hierarchy of control. What do you think we can do at this point, if anything, to increase education for the public?
I don't know. That's a real MPH question. And I got my MPH 30 years ago. That's 35 years ago. I don't know. I haven't, just not to be facetious, I haven't thought about really sort of public health strategies and policies as to how you would, message things, as to what you would try and do to encourage people to do things. I'm sure there are people who are better positioned than me to sort of offer their thoughts about it. It's just not my area, is what it comes down to. I encourage it, but they're not calling upon me to formulate strategies. Like, you're the only reason, Nick, I was called to do the seminar.
So I think that those are all the, that's all the, oh wait, we have one more question. If an N95 mask is used 4 to 5 hours per day, every other day, or every third day, how long can it be used before it's no longer effective? Asks Tara.
So, the effectiveness, my personal experience on reusing a mask, the effectiveness stops when one of the straps breaks, which it invariably does eventually. So the thing is, in the normal environments that you wear, people are not wearing these in coal mines, they're not wearing them in foundries and highly polluted atmospheres, where you have a lot of dust in the air. So it's not like there's a lot of particulate building up on the filters. What happens when particles build up on the filters is you get a filter cake, and now you increase the breathing resistance through the respirator, and so it becomes more uncomfortable to breathe through. And that's the rule of thumb is, if it becomes uncomfortable to breathe through, change the respirator. But if you're just walking around in the ambient air, that's a pretty low concentration of particles in the ambient air, in terms of mass concentration. So you can wear these respirators for a long time. Now, does the structural the filter is not going to wear out. Does the respirator become deformed? Because it's like an N95 filtering respirator. You can crush it. You can deform it. It does get moist. Maybe that sort of leads to deformation too. So they're not going to, eventually they aren't going to fit very well because they become too deformed, but that's sort of like a matter of judgment that you have, how do you think it's fitting your face? You're not going to be doing a fit test on it yourself. The kinds of, quote, fit checks that are often, fit checks are sort of quick tests of leakage outward or inward on the respirator. You can do these on these elastomeric face pieces. I think it's a joke to try and do them on these filtering face piece respirators. So, I say you try and treat the respirator carefully. If you find that it's kind of not fitting snugly when you put it on any longer, then it's time to go. And in terms of, disinfecting, this is another issue, how can I disinfect my respirator? What I do is I take it and I leave it in the sunlight. I'll let the sun shine through my window and I just basically leave it in the sunlight and I'll let it sit there for a couple of days.
Cool. I think that does it. So with that, unless there are any other questions, I think we'll close out. Thank you, Mark, and thank you everyone for coming. Thanks, Mark, for staying after, and thank you for all of you who also stayed after, which were quite a few of you. It's really nice to see all. I don't know if you've seen the attendee list, Mark.
I have not.
There are a lot of former students on here that a lot of them are saying hi.
Oh, okay, that's great. Okay. I'm not dead yet.
Yeah, so Mark does have a pizza being delivered to his house. It's already there. If you want some of it, message me and I'll send you his address. All right. Well, with that, I guess we'll sign off. Thank you, Mark.
Okay.
And thank you, Maya, for organizing all of this. And thank you, Arnie, who was able to take a day off today from hosting, but is usually the host here.
Okay, I'm signing off. Thanks a lot.
All right, take care.
All right,
bye.
Bye.